Okay, very good. So I think it's time to start, right? This is like session E5, so LICS session E5. It will last 1 hour from now to 4:30. I'm Ugo Del Lago. I'm the chair of this session. So there are 6 presentations scheduled in this session. Each of them will take 10 minutes, and the protocol is more or less the following one. At the beginning of each slot, one of the authors will present like a summary of his work, his or her work. It will take like about 2-3 minutes, and the rest of the slot will be devoted to questions coming from either the other speakers or the other participants to the session, or if time permits, like Slack questions coming from our, our Slack installation. So let's start with the first speaker. First presentation. This is this will be given by I think Andrea Vezzosi, and the title of the talk is Partial Univalence in N-truncated Type Theory. So Andrea Vezzosi, you can share your screen if you like, and go ahead.
Yes, thank you. Right, so this is a joint work with Christian Sattler, and I have just a few slides. So this article is about answering this question. While it's well known that UIP, uniqueness of identity proofs, is in contradiction with univalence, because, for example, you have 2 proofs that the Booleans are equal to itself. It's not known whether you can still have uniqueness of identity proofs, but have a restricted form of univalence, where you allow kind of to turn an equivalence between types into an equality only if the 2 types are propositional. This a priori is not contradictory, because, well, there's going to be at most one way to prove that 2 such types are equivalent. So you're not adding more than 1 proof of equality between these 2 types. And more generally, can we have this form of restricted univalence for, instead of propositions n-1 types, while assuming that in general types are n-truncated, so also the universe? Well, the answer is yes, and that's what we prove in this article. Specifically, what we do is we consider a type theory with the usual type formers, pi, sigma, W types, natural numbers, and hierarchy of universes, and also including n-truncated higher inductive types. And we show that these 2 principles, that every type is n-truncated and univalence restricted to n-1 types, are consistent, right? You have a model with all of these features. And the way we build this model is by building by building a universe VL as a higher inductive type in some other model of full homotopy type theory with univalence for all types. And then we show that this higher inductive type V can model all the types we expect, and by an encode-decode argument, it's n-truncated, and but also models this restricted form of univalence. Okay, yes, and the UIP case is done by, of course, taking n equals 0. Thank you.
Okay, thank you very much for the summary. Is there any questions from the audience, from other speakers, from other participants in the session? If so, please speak up.
Yes, one thing I wondered is, I mean, the pop case is certainly very useful, but are there other instances where you want to cut a bit higher, which are also have some useful applications, let's say?
We didn't figure out such a case, right? We mostly realized while doing the proof that the specific truncation level used didn't matter. So it was fairly easy to generalize to all ends.
Okay.
I have a question.
Stephen has a question. Please go ahead.
It's more of a hair-splitting comment. The statement of consistency in the theorem should really be a relative consistency with respect to full univalence, just so it doesn't create the impression that one might prove the consistency of univalence kind of stepwise using your result. You assume that full univalence is consistent in order to prove the partial univalence.
Yes, that's true. Yes.
I have a question.
Yes, please.
Can you elaborate on why this wasn't already known, at least in the case n equals 0, from like set models and so on?
Well, so in set models, what you might have is that, for example, you might have a version of this that's fairly close, but not quite. And so, for example, if you could have a universe of propositions, right? And say, okay, if they are logically equivalent, then they're equal. That's something you could model in the category of sets. But at the same time, you have that two different singleton sets. Two singleton sets can be different, right? You can have two different sets of cardinality 1. So both of those will be propositions in the sense that any two elements of those sets will be equal.
But couldn't you do something like take your universe of sets to be skeletal, like take it to be the set of ordinals or something?
Maybe. I don't know how you will then show the other features of I mean, the fact that this that you have these other type formers in that specific universe, and whether you could create a hierarchy of those. But otherwise, maybe yes.
Okay. Other questions from the audience? Okay, if not,
yes, sorry.
Yeah, this guy,
else?
please. Yes, please.
Oh yeah, because I already asked the question. So, so you said it's not clear what is constructive interpretation of this truncation principle. I didn't really understand what the issue is there.
Sorry, can you elaborate?
I think in your talk you said, let me just get it, that it's not clear what the computation rules for n-trunc are.
Oh, right. Yes. Yeah, that was specifically in the context of a cubical type theory with these features. And yeah, it's simply that one would have to work out for each type how that proof would look like, right? And specifically for the universe, since in the model this is given by an encode-decode construction, how would you want to internalize that? We haven't worked on how exactly it would be best to do that.
I mean, I thought if, like in the propositional case, we can have a static universe of propositions, and so on. We can have static universes of sets and so on. Okay, that's not exactly what you're doing, but that would be certainly not cause any problems with the operation, with the computation, right?
Well, you still want I'm not sure. I mean, how do you prove internally that your universe is zero truncated, for example, right?
Because its HOMs are strict propositions. So hence, by this nature, they are zero truncated.
Okay. Yes. Yeah. If you introduce the concept of strict propositions, and you make sure that your HOMs for your universe end up in that. Yes. But here we were considering the case where you don't have such dedicated kind of static universes.
Sure.
And then what would be a good way to introduce zero truncatedness for these V's?
Okay, yeah, that makes sense.
Okay, I think it's time to switch to the next presentation, which will be given by Thorsten Altenkirch. The title is "The Integers as a Higher Inductive Type." So please go ahead, Thorsten, with your summary.
Thank you. Maybe I do share the screen just to show my email again, because everybody wanted to go on reading my email, I thought. Okay. So let's do this. And where is my talk? Okay. Yeah. What is this? How do I do full screen? Okay. Okay, that's to remind you. This paper was called "The Integers as a Higher Inductive Type," and I was a bit concerned. I mean, I thought it sounds a bit like, oh, these people doing HOT, they don't even know what the integers are, and HOT is so complicated that they have to reinvent the integers, yeah. And so I tried to pay some effort to say, no, HOT is very cool, yeah. And you really want to have HOT, because what you want to do structural mathematics, and you want to do it constructively. And I think both of these things are very, very natural, certainly for computer scientists, but also for mathematicians. But then, once we do this, once we accept this idea that we really want to do structural mathematics, structural constructive mathematics, then we may have to revisit things we already take as granted. And I found this actually quite fascinating. I mean, to look at the integers again. And so in this, if you watch the talk, I give different presentation of the integers. So it's like, I think there are 5. Are there 5? No, 5. And I even have a cube as well. So then the main result is that the sort of, I think, pragmatic, which I find the best definition of the integers, which interacts well with higher types, yeah, which because if you have higher types, you want to be able to use them as like first-class citizens and mix integers and these types with complicated equalities. But if you want to do this, you have to revisit and think a bit more of how to define the integers. And here's the definition we use in the paper in the end. And then you can show that these are actually isomorphic to the sort of signed integers, but they have these better properties, better elimination principles. So that's the content of this paper. And maybe a bit to make a bit of a context, there are this problem shows up in HOT lots of times. Do I say something? So these coherence problems show up, and this was like for me was like for us it was like a nice sort of canonic example of how to study this these sort of problems, yeah. And another example of this is when you define type theory internally using quotient inductive types, as we did in a Popple paper not so long ago. Then you have also the problem that you can either take the steam hammer and truncate the syntax, but then you cannot actually give the standard model, the set model, even, or you start introducing some coherence principles and solve this problem, and that's actually a subject of ongoing research. Okay.
Okay. So thank you very much, Thorsten, for the summary. Questions from the audience, from other speakers?
I have a question.
Yes, please.
Yeah.
Thorsten, in your talk in the beginning, first you did the signed natural numbers, the more familiar presentation, and then you said, oh, this makes it so hard to prove basic arithmetical things like distributivity of multiplication over addition. It gets very complicated. So in the end, your hit definition as the free type with an automorphism, maybe pointed type with an automorphism, did you try to prove the basic arithmetical properties of the integers using that definition? And is it easier to prove the distributivity of multiplication over addition using that specification?
Yeah, no, we haven't actually done this. I looked at some very basic properties, and they're very straightforward. So actually, I didn't use this definition, which has these two predecessors. So, but I used the other one where you have just one predecessor and a coherence law. And in a way, what I like about this is if you define everything, you define, for example, addition, and then you just add a case for the negative numbers. I mean, you add not negative numbers. Sorry, you add a case for the predecessor, and so it seems to be very natural that this is. I haven't really investigated this, but if you look at the proofs and construction for the natural numbers, and then you basically add the predecessor case. That then the coherence principle comes basically for free from this constructive definition. That was my impression, but no, it's a good point, and I'm looking for a student to sort of execute this plan. Okay, but I haven't actually done it. No,
it would make for a better dramatic arc for your talk because you gave an example in the beginning that was hard, and then you show how to. Anyway,
thank you. You found the dramatic shortcoming of my talk.
That's right.
Okay, thank you for the question. Other ones from the audience?
I have a question.
Yes, please.
This is very nice way of thinking about the integers, but can you say anything about computational efficiency? Because it seems like all these representations are still unary, essentially.
Yes, so that's the point. No, you mean maybe we should look at binary integers, right?
Maybe.
Yeah. No, I mean we know for the natural numbers we can give inductive definition of the binary natural numbers. But no, I haven't looked at binary integers as a hit. But that's an interesting idea.
Okay. Other ones?
I also have a question.
Yes, please.
So I mean, I think it's convincing that this representation of the integers is useful if you want to prove propositional properties of the integers. But is it also useful if you want to inhabit general type families? Because it might be that P3 is not equivalent to P4. So then what are you going to do? I mean, it seems like you cannot really apply this.
No, you're right. So we need. Hang on. Let me take the ones which I like. No, that's not the one I like best. This is the one I like best. So yes, you have still to prove this coherence property, and again, I have to say we haven't fully explored this. But I mean, you don't have to prove anymore that the target is a set, right? So yeah, it's a good idea to look at more examples, whether this coherence property, which we have here, is a natural or easy thing to prove. So I haven't investigated it, but it seems to me that it should be quite natural that this property holds. So in particular, if you translate Sag and Pret with an equivalence, then obviously this is just the defining property of an equivalence. So it should be quite natural to eliminate into a set with an equivalence. I mean, that's a basic idea.
No, so what I meant is if you want to construct some function which for all integers n gives us something in Pn, and Pn, I mean, in your examples, Pn happens to be a proposition, but maybe this is not the case for other examples.
Sure.
I don't know. I mean, maybe I'm wrong, but it seems to me that this just doesn't work in this way anymore if P3 and P4 are simply not equivalent.
What P3 and P4? What is P3 and P4?
Okay, maybe I need to think about this
so?
again. I mean, just an example. Like if you just use the integers.
Oh, P3 and P4 are the numbers. Okay.
Yeah. I mean, like P is some type family over the integers.
I see. And now you say you may have that P3 and P4 are not equivalent, and I'm asking it to be equivalent.
Yeah, that's basically the thing that I'm saying.
Okay.
So, I mean, okay, in summary, I thought it's very plausible that this definition of the integers is helpful if you want to prove propositional properties of the integers, like commutativity and so on. But as soon as you want to inhabit type families over the integers, it seems to me that this doesn't work very well anymore.
Yeah.
Because like for like the canonical representation of nut plus nut, for example, it's enough to construct a function from P of 3 to P of 4, for example. But now you have to show an equivalence, which seems to be much harder or even impossible.
Okay.
Okay, thank you very much.
Have you got a concrete example, by the way? I mean, that where you want to eliminate into a type from the integers, but you cannot do this. We can take it offline. Sorry, but that would be interesting.
I mean, like for example, you want to factor a natural number into prime numbers. Then the solution is not a proposition, right?
Yes. But the equivalent should hold, right?
No, I don't think so. Because different numbers have different, I mean, non-equivalent types of factorizations.
Okay, no, that's a good point.
Okay, so I think it's better to switch to the next presentation and leave this question for offline discussion. Okay, so the third presentation will be given by Andras Kovacs, and it's the title is Large and Infinitary Quotient Inductive-Inductive Types.
Okay, a moment.
Yes. Okay. Please go ahead.
Okay. Hello, everyone. The title of this paper is Large and Infinitary Quotient Inductive-Inductive Types. This is joint work with Ambrus Kaposi. So just to give a very short overview of the content. So QIITs are kind of a very general class of inductive definitions, which also allow equality constructors. But this is a bit different from the general case of higher inductive or higher inductive-inductive types, because we say that there are no relevant higher equalities in semantics. So concretely, we do semantics in some extensional type theory where identity proofs are unique. So let's take a look at an example for an infinitary quotient inductive type. So here we have a tree which has a leaf, and it also has a node constructor, which basically has this countable branching with this natural number domain. And we also have some equation which says that we can essentially shift all the children in some particular node to the left, and we still have the same tree. So this is one example for an infinitary QIT, and other examples are formulations of real numbers and also some formulation of ordinal numbers. And in this case we get the infinitely branching structure because we have to represent the limits in a way which is similar to this infinitely branching node. And okay, let's also take a look at an example for a large and also infinitary inductive type. So here we have this type of trees, which has a node, but the node branches over an arbitrary small set. So we can pick any set, and then we can pick a function from that set to tree, and then we have a tree. So an example for this kind of inductive types is, for example, serial numbers and also the cumulative hierarchy of sets from the homotopy type theory book. Actually, both of these examples are from the homotopy type theory book. Okay, and how do we specify the syntax of these signatures? So if you look at these signatures, then they basically look like just listings of types. And that's what we do. So we say that the signatures are just typing context in a particular type theory, which we call the theory of signatures. And so these are just a context in a type theory. For the semantics, we give a model for the theory of signatures, such that every context is interpreted with a category of algebras, and every type is interpreted as an isofibration. And also interesting things to note is that we are able to construct every QIT from the terms of this theory, so the theory of signatures. And we also have this property that the theory of signatures actually includes a signature for itself, modulo some size issues. So basically we have self-description, but there is also kind of a bumping of levels. So signatures at a given level can only describe the theory of signatures for things at a lower level. And we also, so in this work, we also care about kind of being close to implementation. So this theory of signatures has a really low or small encoding overhead. So basically, even if you're working formally, then the signatures are not very different from what I just wrote here. And we also have that the semantics exactly computes the type theoretic induction principles. And this is interesting if you want to do an implementation in a proof assistant where we really have to be able to compute an induction principle from a signature, which is strictly as expected and not just isomorphic to the desired induction principle.
Okay, thank you. Is there any question from the audience or from other speakers? We have time for that, at least 3 minutes, so please go ahead. Yes, please, Steve. Please.
I can ask a question.
Please.
In the talk, you had some remarks at the end, I think, about the consistency strength of adding such types. Can you say a little bit more about that?
So I think, so what I can say about that is that so infinitary quotient inductive types cannot be constructed just from quotients and usual inductive types. So this was, I think this was shown in a paper by Schulman, and I don't remember who the other author was. It was about the semantics of higher inductive types, and there was some Lamstein, thank you. And basically there was some particular example for an infinitary quotient inductive type, which is then shown to be not constructible from simpler type formers.
Okay.
And so basically with this construction, we only show that every large infinitary QIT is constructible from a single large infinitary QIT, but it still remains to show that that particular large infinitary QIT can be reduced to some simpler type formers. And so this is future work. And I think
conjecture, yeah.
my conjecture is that there should be some very simple infinitary quotient inductive type, which is kind of a generic choice principle, and probably then we would be able to reduce every infinitary QIT using that particular generic infinitary QIT. But I don't know what that would be.
Thanks.
Okay, thank you.
Actually, I have a related question, which actually
Yes,
is also a comment in a way, because it being unprovable doesn't mean anything about the strength, right? So Steve used the word strength, but I don't think strength should really matter because, and this is a question, do you think that we can model this in the Set-Quotient model? I mean, I think we can usually model quits in the Set-Quotient model, and that would also show that this is not in an extension of strength.
Oh yeah. So I think so it is true that if you are working in the Set-Quotient model, then the infinitary QITs are constructible. But this is some ongoing research with Ambrus and other students at my university. But yeah, so if you are working in Set-Quotients, then infinitary QITs are constructible.
Thank you.
Thank you. Maybe there is time for another quick question. Otherwise, we will go to the next presentation. If not, let's go to the next presentation and thank us. Okay, so the fourth presentation of this session is entitled Algebraic Models of Simple Type Theories, a Polynomial Approach, and it will be given by Nathanael Arco. So if you can share your screen.
Thank you. So this is joint work with Marcello Fiori. So in our paper, we describe a framework for simple type theories, and we call a simple type theory some structure that has algebraic type structure. It has a term structure which can bind variables, and it also has sorts according to the algebraic type structure. We have substitution on terms, and the types and terms can both have equations on them. So we want some way to describe these simple type theories. This means giving both syntax and semantics to them. So on the side of syntax, we have presentations that are given by natural reduction rules in a formal sense. So these coincide with the usual natural reduction rules that are often used to present simple type theories. And we show that these natural reduction rules induce polynomials. And these polynomials further induce polynomial functors, and the algebras for these functors are going to be models of the simple type theories. So there's a very elegant correspondence between the syntax and the semantics in this sense. So on the side of the syntax, we have models in pre-sheaf categories, where the base category is a category of contexts, as is familiar with approaches to type theory. And the structure of the terms is given by algebraic structure on polynomial functors. And these are functors which are induced by the natural reduction rules. And then on top of that, we need to describe substitution structure. So we describe how these categories of polynomial algebras have or can be equipped with a substitution monoidal structure, which interprets simultaneous variable substitution. So simultaneous substitution of terms of variables in a context. And this sort of captures the structure of simple type theories. And then on top of that, we prove a few meta-theoretic results, which show in some sense that this is a good framework. It captures properties that we're interested in. So for one, we can construct initial models for the simple type theories, and these coincide with the syntax. So it has the property you would expect. And then on top of that, we have a general substitution lemma. So this means that you can freely add the substitution structure to a simple type theory. And it's sort of given by the intuitive textual replacement. So you don't have to add any more terms. So you add an explicit substitution operator, just it's not going to add any more terms because everything is equated in the right way. So this is a theorem that often has to be proven manually for different type theories. And so this is one general result. If you can present a simple type theory in our framework, then you get a substitution result for free. And then finally, we give a Lambek style correspondence between models of simple type theories satisfying a simple property and Cartesian multi-categories, which are equipped with structure that corresponds to the algebraic structure on the polynomial algebraic structure on the presheaves, which in turn corresponds to the natural deduction rules. So there's a multi-category type theory correspondence as well. And so this gives a setting in which you can talk about the syntax and semantics of simple type theories in a sort of cohesive way. Thank you.
Thank you very much. Are there any questions from the audience? The speakers. Okay, I can ask one. I was quite curious while looking at your video about the following. Do you think we can kind of slightly generalize your framework in order to account for concepts which are, typically, which are very typical in type theory? For example, like the normalization in natural deduction, for example, the process of normalization. Could we kind of start building a general theory of normalization inside your framework and talk about things like strong normalization properties or things like that?
So I haven't thought about this at all, but I can sort of think of, I think there's a plausible direction in which it could be taken. So I imagine you'd probably want to replace the equations with some sort of rewrite or reduction.
Absolutely, yes. I was thinking about the rewriting, yes.
Right. So I've definitely spent some time thinking about using rewrite rules instead of equations. And I think I know how to do it. So I think that can definitely be done. And then I'd hope that you could get some general normalization results using things like gluing from the literature, which is often applied to very specific type theories, but I'd hope they could be applied to in a setting like this, but I haven't tried it yet.
Thank you.
I can add something to that.
Yes.
Because you have proven initiality, then you can use an argument from gluing, the fried cover type argument, which is a standard way of proving at least canonicity, if not normalization results. So I think that's actually a nice thing a nice application of your setup. You have this initiality theorem, and that has some power.
Right, thank you. Yeah, well, I know Marcelo thought a lot about that side of things, so he probably has some ideas there as well.
Yeah.
Actually, sorry, for normalization, you need a variation of gluing, but that's another story. Actually, I wanted to ask a question. Maybe aware with Ambush Kaposi, we have presented sort of intrinsic syntax of type theory, actually with dependent types, using quotient inductive types. So I wonder how your approach is related to this. Let me say what I think. So, I mean, we can do this for simple type theory as well. But as you point out, then you have these substitution laws. We have to have equations basically that every term former is natural, and you sort of subsume this. So all the term formers are sort of automatically natural. Is this the sort of main difference? Yeah.
Mm-hmm. That is the case. All of the term formers commute with substitution appropriately to make that work.
So in a way, what you do is almost like you can work in a kind of a higher order abstract syntax, it is called, to prove.
Yes. So it's it's really second order abstract syntax.
Yeah.
But using second order abstract syntax, you can represent higher order structure. So it suffices.
Okay, thank you.
Okay, so I think let me see, just 1 second. Yeah, I think Alex Cabos, who is present here, would like to explain the question he posed to Nathanael on Slack. So please.
Hello.
Yeah, please go ahead.
Works good. So I don't have much to explain, but the question is, we've got CCCs, we've got the multi-substitution algebra, and we've got the Cartesian multi-categories on the other hand, with or without exponentials, probably with exponentials for simpler type lambda calculus. And I mean, the answer is probably yes, but the question is, what is the exact relationship between all those? Are there any devils in the details?
So once you restrict to the models of simple type theory that have the sort of the free context, and so you can do, so single variable substitution is the same as multiple substitution, then you get an exact corresponding equivalence between the category of models for the simple type theory corresponding to the simply type lambda calculus and the Cartesian multi-categories that are closed appropriately, and the product type constructor is going to make the Cartesian, well, no, the non-representable Cartesian multi-category structure representable. And so these are then equivalent to the CCCs. So you have to apply a restriction on the context. So it's similar to the democracy in things like categories of families. But once you do that, then you get the equivalence.
So then essentially all these three things, if you play your cards right with respect to the context structure, are very much the same presentation of the same thing.
Right, yes.
Okay.
Yeah, different perspectives.
Thank you.
Okay, thank you very much. So I think it's maybe time to switch to the next presentation, which will be given by Matthew Weaver, and the title is A Constructive Model of Directed Univalence in Bicubical Sets.
Yeah.
Please go ahead.
Okay. So as a quick condensed summary of our paper, so directed type theory is an extension of homotopy type theory, in which we add a notion of directed paths to the existing notion of indirected paths, and we'll call these morphisms. And at a high level, what this means is that types are now going to be infinity-1 categories instead of infinity groupoids. And with this new notion of path, we also get a new notion of univalence. And for directed paths, we want directed paths in the universe to be equivalent to function types. And in this type theory, we have a universe of covariant vibrations, which contains types that themselves have only trivial morphism structure, but they defend covariantly on the morphisms in the context. So in particular, if you have a morphism in the context, you can transport covariantly along it in the universe, but only in the same direction as the morphism. And this universe does have directed univalence. And so effectively, it ends up being the infinity-1 category of infinity groupoids. And so this version of directed type theory has been worked out previously in a classical setting. And in our paper, we translate it to using ideas from cubical type theory and are able to make a constructive model of this theory. So that's.
Thank you. Thank you very much. Questions from the audience, from other speakers?
Sorry, I mean, it seems I'm the invariant question.
No problems, please.
First of all, I really like this example. I think it was really a good thing with the untitled lambda calculus. I got a bit confused. There were a little bit too many universes for my taste. So I understood this UCOF are the covariant things. So they correspond, they can be interpreted as categories, right? And then you had this U Siegel, and my impression was this were with the groupoids, but maybe I got this wrong.
Okay, so the covariant universe contains only groupoids, infinity groupoids. Yeah, so that's why we need the Siegel universe, because those are the ones that are infinity categories.
Yeah.
Obviously, we want to have categories, but as it is now, directed univalence doesn't work in the universe that contains.
Okay, so I got confused there. Okay, and this UCOF stack, which you have in the end, is this just an improvement on UCOF and replaces it, or do you have UCOF?
So it basically replaces it because directed univalence doesn't actually, we couldn't get a constructive version of it directly on the covariant universe. We need this extra structure we get from restricting it to stacks to basically complete the proof. And it doesn't really change anything from the top level perspective because all the type formers we care about also satisfy this extra condition.
But you really have to go one level higher so that things work out.
Exactly. I just did some extra structure we had to use.
Okay, thank you.
Thank you very much. I think Stephen has a question.
I have a question. I have my typical question. Let me first say that I'm very impressed by the mathematical sophistication that's used in this paper. It's really a tour de force.
Thanks.
You're welcome. My question is, when you use it's a little bit technical, but it's in your talk. So when you use the Kobar construction, you seem to be working semantically, and then you say, okay, now we add the Kobar construction. Here are some laws that it satisfies. I wonder, are you really adding the real Kobar construction, or are you just working axiomatically saying, here's an endofunctor, it satisfies these conditions, that's all we need to know about it, and then we proceed axiomatically?
So from our perspective, we're working axiomatically. With kind of taking what, because in particular, we're using this syntactic version of Kobar that's been defined by Kakan, Sattler, and Roosh. And so using kind of their syntactic axiomatic version, we're able to get everything we need. And I think they're in the process of actually connecting it to the real Kobar that kind of we're used to. But from our perspective, it's just,
it's kind of a type theoretic approach to Kobar, which you call Kobar because it has some same formal properties. Is that fair?
Yes. Yeah. Yes.
Good. Well
okay. Other questions? We have a little bit of time, so please go ahead.
Well, okay, I have one more.
Yes, please.
In the undirected type theory in HOT, the challenge, or one of the most difficult things, is showing that the universe is Kahn. So here, I guess, analogous problem would be showing that one of those universes, maybe the covariant universe, is actually a stack. Are there some special difficulties with that, or?
Yes.
Is it
so
parallel?
So that's the one thing that we're still investigating that. Basically.
Gotcha.
Because we don't, like, in particular, in an ideal setting, we would be only considering stacks. So it'd be like the two universes would be like the UConn stack and UCov stack. But we thought it was easy, then we realized that there's a little bit more to it. So for now, we're thinking about UConn and UCov stack until we can work that out.
Okay, interesting.
Okay, thank you. So if there are any other questions, please speak up. Otherwise, we will switch to the next presentation. Okay, so thank you very much. Let's go to the last presentation of this session, which is entitled Coherence via Well-Foundedness, Taming Set-Quotients in Homotopy type theory. And it will be given by Jakob von Bräumer, I think.
No, by me. Sorry, by Nikolai.
Ah, I'm sorry.
Yeah, I have some.
I'm sorry
with the interface, but you can see my slides, right?
Yes.
Okay, great.
Yes, we can.
Okay, thanks for the introduction. So this is just a subset of the slides that Jakob has used in his presentation on YouTube. So the starting, I mean, so this project is essentially about the following problem. Let's say we have some graph, like this graph, which I have shown on the slide, and we want to show a certain property for all closed zigzags in this graph. So now by closed zigzag, I just mean any zigzag, which I mean can use, it can go through vertices as many times as it wants. There's no restrictions, just it has to be a sequence which ends at the same place where it starts. And yeah, so we want to prove a property about such closed zigzags. Now, if we did not have this condition that these zigzags have to be closed, then the straightforward approach to prove such a property would be induction, right? But since we only care about closed zigzags, well, closed zigzags are not inductively generated, so we cannot do induction. And this becomes much more tricky. So now we don't want to solve this problem in general. We make simplifying assumptions. The first one is that this graph is locally confluent in the sense that if you have a local peak or a span, like the red two edges, directed edges, you can complete them to, you can complete them in the usual way, how confluence is defined. And the second assumption is that this graph is Unitarian or co-well-founded in the sense that there's no infinite sequence of morphisms. Well, of course, we want to formulate this in a constructive way, but in most cases, it actually doesn't matter. I mean, in most applications, it doesn't really matter. So the intuition is no infinite inductive decreasing sequences. Okay, so why is this in the type theory session? So the reason why we got interested in this situation is that sometimes, I mean, if you work in homotopy type theory, you very often have to show some coherence questions. And now it could be that this graph represents a relation. And we want to take the set quotient of this type of vertices by this relation that is given by the edges. And so now, depending on what you want to do with the set quotient, but the set quotient in particular means that it's set truncated. So if you want to construct functions from the set quotient into some higher type, you, well, as you expect, you need to prove some coherence conditions. And if the codomain is a one type, then this coherence condition can be formulated by saying that every closed zigzag is mapped to a trivial equality, right? The condition for set quotients into sets is that every edge is mapped to an equality. So if we map into one types, then we also have to say that every closed zigzag is mapped to a trivial equality. Okay, so how are these assumptions of local confluence and Unitarianness justified? So in the examples that we have, these assumptions seem very natural. So for example, if we take this question of free groups, so the free group over some type, maybe with non-decidable equality, can be constructed by taking lists lists of elements of the set or type, where each element is positive or negative, and then you construct the relation which says that two such lists should be considered equivalent if one can be constructed from the other by deleting radix, like a pair of elements which cancel each other out, like here in this example. And it's quite easy to see that in this case, this relation is really locally confluent and also Unitarian. You cannot, in this case, you actually know how often at most you can reduce before you reach a stage where you cannot reduce anymore. Okay, so now how do we approach this problem? The basic idea is simple. If you have some closed zigzag like the one that is shown here, you can find a local peak or a span like the one in red here, and you can use local confluence to split this big cycle into two smaller cycles. So now on the left, the left subcycle with A3, A2, A8, A9, A4, that's the shape that we get from local confluence. And the cycle on the right side, where it looks like it's bigger because it actually has more vertices. But if you use the subset, the multi-set extension as an order, then this cycle on the right-hand side is actually smaller than the original cycle. And you can show that this process of splitting your cycle terminates, in the constructive sense. So yeah, you split cycles into smaller and smaller cycles. And from this, we get an induction principle, which approximately reads like this. So you have this relation on a type, and this relation is locally confluent and Unitarian, and you have some family indexed over type over cycles, and you want to construct some element of this family for every cycle, then you only have to do it for the empty cycle and for these shapes that you get from confluence. And then, well, you also have to know that this family P is stable under rotating cycles and merging of cycles, but these are very natural properties which are satisfied in all examples. And yeah, so then our derived induction principle says that yeah, you get some element in the family for every cycle. Okay, yeah, so Jakob has formalized all of this in Lean. It was quite some effort. Yeah, so now we are aware that the half of our paper is actually not about homotopy type theory, but it is about formalizing some rewriting, some ideas that could be relevant to rewriting. We are very grateful to Vincent von Ostrom, who has given us very detailed remarks, and which might lead to more applications of this principle in areas maybe even other than homotopy type theory. Yeah, but this remains to be seen. Thanks.
Thank you very much. Okay, so we have time for maybe a couple of questions. So if the audience has any, please go ahead.
I'll ask a question.
Yes.
In your talk, or in Jakob's talk, you mentioned an application to the question of whether the usual construction of a free group on a set is actually a one type. Or no, a zero type, right? And you have an approach using the loop space and so on. But I didn't get whether you actually solved the problem or you made some steps towards solving the problem or something like that.
The only oh, sorry, do you want to answer?
I don't care. the only approximation that we do solve is that the one truncation is a set. So we are only making a statement about the first stage level. And the other problem still remains open.
Yeah, so the general problem is whether the free group is a set, and we only show that the fundamental group of the free group is trivial.
Mm-hmm. Okay.
Sorry, yeah, also comment, this is obviously related to our talk.
Exactly.
So there we show that the free group with the one generator, which are the integers, are set. And this argument can be generalized to the free group over any set which has a decidable equality. So that's easy. So classically, then this problem is already solved. But if you're constructive, then there's a problem to show it as was pointed out for sets, a free group over a set, which may not have a decidable equality, whether this is still a set. And this was also subject of some earlier paper with Nikolai and myself. So I think what has happened here is that this is that now a more generic approach has been developed, which hopefully will be also applicable to other problems. I hope that's a correct summary.
Yeah, so our old paper had some approach which was really tailored to the specific problem of the free group, and it was a huge hack. And I would say it was a huge hack. So the construction which we have now is much more general and also much nicer, I think, and applicable to other similar problems, like yeah, this more general question, if you take a push out of sets, whether that will be one type, and yeah, questions like this. I also hope that it could be applicable to the situation that Thorsten talked about before, with the representation of the syntax of type theory. But this is more tricky because there's some induction involved going on.
Okay, thank you. Maybe one quick question to end the session, or maybe even questions from the audience about other talks. Okay, if not, I think we can end the session now. I thank all the speakers. I also thank a lot people from Saarbrücken who helped us technically and as moderators. And yeah, we'll see you around at LICS or ICALP tomorrow. Yeah, see you.